Hello and welcome to another pre-calc video. This video is going to cover section 2.2, polynomial functions of a higher degree. And we've got 4 bullet points here. Use transformations to sketch graphs of polynomial functions. Use the leading coefficient test to determine the end behavior of the graph of a polynomial function. Find the zeros, the real zeros of a polynomial function, and use them to help sketch. And then the last thing, we'll be using this intermediate value theorem to help you locate real zeros of polynomials. Or sometimes you might not be able to actually locate them, but this intermediate value theorem will tell you that they do in fact exist. Let's dive in. In this section, you will study basic features of graphs of polynomial functions. One feature is that the graph of a polynomial function is continuous. Essentially, this means that the graph of the polynomial function has no breaks, no holes, no gaps, as shown in the figures down here below. The second figure on the right is an example of a piecewise function that would not be continuous. Another way to think about continuous is, can you draw the graph without ever lifting your pencil off the paper? So I'll start down here, and using red ink, I can draw this graph, and I never once have to lift my pencil up. So that is a continuous function. If I try that on the B graph, I'm working my way along here, and I get to the end, and I have to lift my pencil up to get down here to start the next piece of the graph. So continuous, means it's just a smooth, uninterrupted function. And any polynomial is going to be continuous, like x to the fifth minus 4x cubed plus 2x plus 3. As long as there's no division below, if it's just a regular polynomial, they're always continuous. And then the book continues. Another feature of the graph of a polynomial function is that it only has smooth, rounded turns. The graph of a polynomial function cannot have a sharp turn. See here, these are nice and smooth curves. You cannot have sharp turns like this, a V-shaped graph like the absolute value graph. Okay, so here on the left, polynomial functions are graphs with smooth, rounded curves. Functions with graphs that have sharp turns are not polynomial functions. Sketching graphs of these polynomial functions of degree greater than 2 is often more involved than sketching graphs of polynomial functions of 0 degree. First degree, that would be a straight line or a parabola. However, using the features presented in this section, along with your knowledge of point plotting, intercepts, and symmetry, we should be able to make reasonably accurate sketches by hand. The polynomial functions that have the simplest graphs are monomial functions of the form base x to some power n. There's no other terms after it. There's no plus or minus a constant. N is an integer that's greater than 0. That would be our exponent. When n is an even number, x squared, x to the fourth, x to the sixth, the graph is similar to that of x squared. When n is an odd number, the graph is similar to that of x cubed, as shown in the figure here below. Moreover, the greater the value of n, the flatter the graph nearer the origin. Polynomial functions of this form are often referred to as power functions. So here in the graph on the left, the gray graph is the basic x squared. And then we have here in the black ink x to the fourth. Any x to the even exponent is going to have this general shape. The higher the exponent, we might get a flatter spot to the graph here, but it will rise much quicker. Here x to the fourth is inside the x squared parabola after the point 1, 1. And any higher power, x to the sixth, would be even closer, x to the eighth. The higher the even exponent, the closer we get to the y-axis. And notice they share that point here, 1, 1, and negative 1, 1. Because anything to, 1 to any power is going to equal 1. Here in gray ink is the x to the third graph, and then in the darker ink is x to the fifth. Here again, we're a little flatter around the origin with the higher exponent, but after the point 1, 1, we're going to be inside the x cubed graph. So here's our x cubed, x to the fifth, seventh, ninth. They would all be going closer to the y-axis. And then here we've got that origin symmetry. The same thing's going on down here in the third quadrant. So basic shape, x to the even exponent is going to look something like this. X to an odd exponent will be going up in the first quadrant and down in the third. So here we get to our first example, sketching transformations of monomial functions. And it says sketch the graph of each. So here we've got negative x. Ooh, hold on here. I think we should look at this slide first. I think I might have got these out of order. The leading coefficient oh no, I guess we do example 1 first. Okay. So it says sketch the graph here. Well, no, let's go over this first. This leading coefficient test. You know, we've got this a polynomial here. We usually write the highest exponent first. So that is our first, the highest order of the variable, the highest exponent. That would be the power of our polynomial. And in front of it is our leading coefficient. Sometimes it's a whole number, sometimes it's a fraction. The big idea is it positive or negative. So it says here, as x moves without bound to either the left or the right along the x-axis, the graph of a polynomial function will eventually rise or fall in the manner described below. So when the exponent is odd and it's positive, a sub n, that leading coefficient, is positive, it's greater than 0, it's going to go up to the right and then down to the left. It's going to rise to the right and it's going to fall to the left. But if the leading coefficient is less than 0, that's going to reverse. Let me switch to blue ink. If our leading coefficient is negative, it's going to rise to the left and it's going to fall to the right. Now here, instead of using these book provided things, let me just do this. So if we have positive x to the odd power, it's going to go up to the right and down to the left. If it is a negative x to the odd power, it's going to reverse that. It's going to rise as we go to the left, and it's going to fall as we go to the right. Now, when the exponent is even, if the leading coefficient is positive, we're going to rise to the left and rise to the right. If that leading coefficient is negative, we're going to fall to the left and we're going to fall to the right. So again, think about a parabola. You know, if you just think about the basic x squared or any x to the even power, it's a parabola opens up. If you see something that's a negative x squared or any even exponent power, that's going to be a parabola shape opening down. Okay, and here at the bottom, the dash portion of the graph indicate that the test determines only the right and left-hand behavior. You know, the graph in the middle might be doing some other stuff we're not sure of, but we know in the long run where that graph is going to head. So let's go back and look at example 1 now. Here we go. So it's negative x to the fifth power. So right off the bat, you know, x to the fifth, if it was positive x to the fifth, would roughly go up here and down here. It would go through the origin. If we plug in 0, a 0 would come out of there. But that negative part is going to flip the graph. And let's do a couple other points. So we do know 0, 0. And then if we put negative x to the fifth, that's going to open up to the left. So if we put negative 1 in there, f of negative 1, negative 1 to the fifth, that would be positive because we've got our negative in there with the 5. Let me write it over here. we're doing negative x to the fifth, and we're putting in a negative 1. So we would multiply that negative 1 5 times. This negative would still be there, and it would hit this negative in the front and turn positive. So here at negative 1, we would be up at positive 1. So, we already established we are going to be going up there. We've just, found another point that our graph is going to go through. And if we put positive 1 in there, remember this was a negative out front. Oops. Our function is negative x to the fifth. So now if we put a positive 1 in there, 1 to the fifth is 1, and then this negative comes in and makes that minus 1. So at 1 on the x-axis, we're down here at negative 1. Letter B, quantity x plus 1 to the fourth power. So because it's to the fourth power, we know it's going to be parabolic in shape, opening up. But remember what goes on inside these parentheses here before we take it to the fourth power. That's a left or right shift. And that plus means we're going to be moving 1 unit to the left. So let me draw an xy axis. And I'm going to do green here. If it was just x to the fourth power would go through the origin and 1, 1 and negative 1, 1. So here's our x to the fourth graph with 3 points on it, 3 interesting points because it's right at the vertex and a couple right close to it. And we're going to move everything to the left 1 unit. So that origin point comes over here. This point shifts over, now it's the y-intercept. And this point that was at negative 1, 1 is now at negative 2, 1. Everything got bumped to the left. And there's our sketch. And what do we got down here? Okay, here's the book. The degree of that's odd, so the graph is similar to x cubed. Note that the negative coefficient reflects you around the x-axis. Yeah, and they're a little bit better than mine. So there's those, again, those at least have those 3 points around there. And in all of these, x to some power, once you find the vertex, you usually just go over 1, up 1, over 1, up 1, unless you've got a coefficient in front. And we talked about those. Here we go. Now here, let's read the directions. Describe the left and right hand behavior of each function. It doesn't tell us to sketch the graphs, but what I like to do, if I just draw a quick little xy axis, I see here that's negative x to the third. Make sure it is the highest power. We don't have a higher power over here. So it's negative x to the odd. So this is going to look like this. And we would say to the left, we rise. And to the right, the graph falls. Letter B. X to the fourth. Highest power there, so that's x to the positive power. It's going to be parabolic, opening up. So I guess we could write this a little quicker. To the left and to the right, the graph will rise. And last one, letter C. X to the fifth minus x, highest power x to the fifth. It is a positive x to the odd power. So it's going to go up in the first quadrant, down here in the third. And we could write that as to the left, the graph will fall. And to the right, that should be, there we go. To the right, the graph will rise. So there, I just do those little sketches. It helps me put it into words better. Here's what the book says. The degree is odd, leading coefficient is negative, so we rise to the left, fall to the right. Oh, again, and here's the actual graph. We're just concerned about the end behavior. We know it's going to go up this way and down this way. We aren't sure about every twist and turn in here just yet. B, leading coefficient's positive. It rises to the right and the left. Positive, even exponents there. And the last one, degree is odd, leading coefficient is positive. We will rise to the fall to the left, rise to the right. Here are some practice problems for you. And here it just says sketch the graph. You know, a lot of all these are going to be parabolic in shape. At least have the vertex and maybe a couple points close to that. And then this one here, you just got to describe it. Does it rise to the left or the right or fall? So pause the video, try the problems, and see how they turn out. Letter A. It's a quantity here to the fourth power, so that's going to be parabolic in shape opening up. And we have in here a shift to the left 5 units. So we're going to go 1, 2, 3, 4, 5. Here we are at -5. And then since our leading coefficient here is 1, just to get to 2 quicker points, we'll go over 1 to -4 and up 1. And we'll go 1 to the left to -6 and up 1 there. And there's our sketch. Letter B, x to the fourth minus 7. So if we look at just this, x to the fourth, that's going to be opening up parabolic in shape. And in here, that -7 is outside. It's not in here inside a set of parentheses. So this is a shift down 7 units. So this is not going to be very good to scale, but I'm going to go down 7 here, this down to -7. That will be my vertex. And then we're going to go opens up. And I will go over 1 and up 1. So here we are at 1, -6, and -1, -6. I guess we could find the x-intercepts by setting that to 0. So we would add 7 and take the fourth root. The fourth root of 7, that's just a little bit more than 1. So we could say our x-intercept is between 1 and 2. Without a calculator, you know, we can't get an even better estimate, but we do know the fourth root of 7 has to be between 1 and 2. And it would be the same thing, a negative reflection over here. Between -1 and -2, we would have another x-intercept. Now letter C is just a twist on B. This B was x to the fourth minus 7. This is 7 minus x to the fourth. If I rewrite it in order, negative x to the fourth plus 7 might make a little more sense. So now it's negative x to the even exponent. It will be parabolic in shape opening down. But this plus 7 is going to move us up the y-axis. 1, 2, 3, 4, 5, 6, 7. So there's our y-intercept. We will open down. And we could do the same thing to find the zeros here. And we could at least say we're between 1 and 2 and -1 and -2. Last one here. Even exponent. We're going to have a shift here to the right of 3 units. So we're going to go out 1, 2, 3. And put in our point. That'll be our vertex, and we're opening up. And you know, usually we would go over 1. Here I'd go over to +2 and up 1 unit to get to this next point. But if we did that here, that point's going to get multiplied by 1/4. So this point would not be at a height of 1. It would be pulled down to 1/4. That fraction's going to flatten us out a little bit. And be the same thing over here at +4. We would have a point up at +1, but the 1/4 pulled us down a little bit. So the graph will look something like that. Still, we got the general shape. Here we're just describing. So highest power, x to the third. Leading coefficient is positive. Positive x to the odd means we are going to rise to the right and fall to the left. Left, fall, right, graph will rise. Letter B, negative x to the odd. So x to the odd, and if it's negative, we're going to go up to the left, down to the right. So left, the graph will rise. to the right, the graph will fall. Now here we talk about the zeros of a polynomial function. It is possible to show that for a polynomial function f of some degree n, that would be its exponents, these two statements are true. The function has at most n real zeros. We'll study this detail more in the fundamental theorem of algebra. The function f has at most that number n minus 1 turning points, turns on the graph. These turning points are also called relative minima or maxima, the point at which the graph changes from increasing to decreasing or vice versa. Finding the zeros of a polynomial function is an important problem in algebra. There's strong interplay between graphical and algebraic approaches to this problem. So if I just made up any polynomial, x to the 6th minus 2x to the 4th plus x cubed minus 7, I could say, using the facts up here, that this function has at most 6 zeros. I take its highest exponent. It has at most that many zeros. Maybe not that many. Maybe it has a couple that are repeated, but that will be the most that it possibly has. And if I'm going to graph it, it's going to have that number minus one more turns. The graph will have 5 turns. That means we could have 5 mins and maxes, in total, maybe 3 mins and 2 maxes or vice versa, but we know the graph will have that many turns. Now here it says when f is a polynomial function and a is some real number, these statements below all mean exactly the same thing. So the first two are pretty close. If I write x equals a, that is a zero of the function f. And I could also write that same thing, x equals a, is a solution to the polynomial equation. If I put that number a in, out pops a 0. Think about when we're solving a polynomial and we get down to one of those last steps where we have maybe a factor like x minus 3 times x plus 4, and we set each of those to 0, and if we set the first one to 0, we'll add 3 and get x equals 3, and here we would add or subtract 4 and get x equals negative 4. This is what 1 and 2 we're talking about. When we get down to x equals a number, those are the zeros of the function, and those are also solutions to the equation. If we remember, for something like this, we would set our original polynomial equal to 0, then we would factor it, and then we would set our each factor to 0. Like this would have been x squared minus 1x, or no, plus 1x minus 12. And we would set it equal to 0 and then get our factors and set our factors equal to 0 to get our solutions. So 1 and 2 here, we're sort of starting down at the bottom. Those are our zeros or our solutions. Number 3 now, let me switch to blue ink. This says parenthesis x minus a is a factor of the polynomial. Well, that's this step right here that preceded it. We would factor our polynomial. These would be the polynomial in its factored form. So that is a factor of our original polynomial. And then we could say, if we wanted to put this in the form of a point, x comma y, since we're touching the x-axis, our y value would be 0. We could say from my example down here that 3 comma 0 and negative 4 comma 0 would be the x-intercepts of the graph. So I could take those and make them into points, and when I'm drawing a sketch, I can really make note of where those x-intercepts are. So again, these things are all equivalent, so it's just the same thing expressed in different ways. In example 3, did we do example 3? No, I guess that's coming up. Yeah. Well, actually, we'll check this back after that. Let me even do this. Oops. There we go. Example 3. Find the real zeros of a polynomial. We've got negative 2x to the fourth plus 2x squared. Then determine the possible numbers of turning points of the function. Well, let's get the turning points out of the way right now. This is negative 2x to the fourth, so we have at most 4 zeros. So when we're solving this, we might find 4 of them. And then the possible number of turning points, just subtract 1 from that number. 4 minus 1 is 3. The graph will have 3 turns. That's supposed to be an R there, T-U-R-N-S. I can spell. So let's find the zeros. We're going to take the function and set it equal to 0. So what can we factor out? I'm going to factor out a negative 2. And I can also factor out an x squared. So let's see what's left. Here I would have an x squared. If we distribute, we would get back to negative 2x to the fourth. We're going to have a sign change, and we factored this out entirely, so there's going to be a 1 there. Ooh, and look at that. That looks like a difference of 2 squares. So that is going to break down into a sum and a difference. X plus a 1 and x minus a 1. So here we have our zeros. If we set this equal to 0, we could divide by negative 2 and get x squared equals 0, and then take the square root. That would be x equals the square root of 0 is 0. If you're thinking plus or minus, 0 does not have a sign. It's neither positive nor negative. It lives in between. Here are the other factors. If we set x plus 1 equal to 0, we get x equals negative 1. And here we'll set x minus 1 equal to 0 and get x is positive 1. So we found the real zeros. These are our solutions. If we put a 0 back in the original, a 0 pops out. If we put negative 1 or positive 1 back into the original, a 0 pops out. And these are points that would help us sketch our graph. Now that slide I sort of skipped over. It says here, note in that example, this negative 2x squared yields a repeated factor of x equals 0. The exponent is even, so the graph will touch the x-axis at that point. And let me even back up here. We could have, when we were factoring this, we could have broke this up into a negative 2x times another x to get the x squared. And we could set each of those equal to 0. Negative 2x equals 0, and we could set the other x equal to 0. So since here it was a power higher than 1, it's a repeated 0. And the general rule is when you're at a repeated 0, you're going to bounce off the x-axis on the graph. So here on our graph we would bounce or not cross the x-axis. These other ones, when we had x equals negative 1 and 1, since these are first power, the graph will cross the x-axis. Cross x-axis. Again, a repeated 0, you'll touch it but not cross. And I think, ooh, it looks like the graph's up here in the corner. There it is. So we do cross at negative 1, we cross at positive 1, but up here, you know, as we're coming down, we do hit at 0, but we bounce off. And those, we can't cross at 0 or the end behavior would not fit. You know, this is a negative and it's x to the even power. We know the graph goes down to the left and down to the right. We know we cross at these. So if we cross here, we wouldn't be able to get back. You know, if I crossed here, I would cross again. I would not be able to get to my end behavior. You know, that repeated 0 means we bounce when we approach that x value. Oh, and here's where the book says that a factor x minus some number a raised to the power k yields a repeated 0 of multiplicity k. Whatever that exponent is, they call that the multiplicity. When that number's odd, the graph crosses at that x value. When that number is, that k value, the exponent is even, you'll touch but not cross. You'll bounce off the x-axis. To graph polynomial functions, use the fact that a polynomial function can change signs only at the zeros. Between two consecutive zeros, that polynomial function must be entirely positive or negative, either above or below the x-axis. This follows from the intermediate value theorem, which we're going to see a little later. This means when you put the real zeros of a polynomial function in order, they will divide the real number line up into intervals on which the function does not change sign. These resulting intervals are test intervals in which we can choose some representative value to determine the value of the polynomial if it's going to be function and the graph is above the x-axis, or negative. The graph then will be below the x-axis. Here's a practice problem for you. Find the real zeros by setting this equal to 0 and factoring it. Determine the possible maximum number of turning points of the graph. So pause the video and have some fun, and then check your answer. Step 1. Set it equal to 0. Now let's see what we can factor out. Every term has an x, so that gets pulled out. And we've got x squared minus 12x plus 36. And that's equal to 0. Okay, x squared, we got a number at the end. It looks like we can factor. Factors of 36, and this is positive, that add up to a negative 12. So these have to be minuses. Add to a negative, multiply to a positive. And what numbers multiply to 36? 1 times 36, 218. 312, 4 times 8, no, 9. And 6 times 6, there it is. 6 times 6 is 36. They adds up to 12. So minus 6, ooh, that's a repeater. So we've got x, and then quantity x minus 6 squared equal to 0. Oops. So if we set this x equal to 0, it's just x is 0. Here, it's a repeater, so we're going to get sort of the same answer twice. If I set x minus 6 squared equal to 0, the first thing I would do is square root, so the square's gone, and the square root of 0 is still 0, and then I'd add the 6. X equals 6. Again, this is a repeater. It is multiplicity 2. Multiplicity 2, so the graph will bounce at negative 6. And let's come up with a good, so we had x equals 0, x equals 6. At 0 we cross, and at 6 we touch and turn. We bounce. So let's see, if I drew an xy axis, it's x to the third, so I know I'm going to go up to the right and down to the left. I've got an x-intercept at 0, and here is positive 6, and this one I'm going to bounce off of, put sort of an x through it. So if I start down here to the left and I'm working my way up, I know that I cross at the origin, and then I'm up here, but I've got to hit this point because I know I hit the x-axis there, but that's a good because I bounce, and that allows me to join up with the end behavior and go up to infinity. And is that the end? The homework will be on WebAssign, or check the class Teams page, and I'll see you in the next video.